to report some work of me and John. So I'm going to start with some motivation, probably motivation for John and co-authors, but maybe not for everyone because it's from Noetherian homotopy theory. So let's start with some motivation. So if you've ever seen John talk, then we have the category of rational G spectra, so the G-equivariant G spectra, and we have the sphere spectrum being the homotopy pullback of this form. So this is the Tate square, which we know as a homotopy pullback and a homotopy pushout even. And if I draw up this other well-known square, it's only two squares.
Did you say it's a pullback and a pushout?
Yeah. Okay. It happens in a stable model category, so homotopy pushouts coincide with pullbacks. We have the Sullivan arithmetic square. We also know is a push-out and a pullback. So I'm going to rewrite this DEF term here. So DEF can be expressed as the product over n of D equal to n plus. And now these two squares are starting to look a bit similar. And then the question is kind of how similar are these and what's the general machinery behind them. So this Tate square here gets used in these algebraic models. So this is work of Barnes. Nope, that's called Greenlees. Elena and Brooke. Subtle, yeah. So what we do is we take this and we say that the category of rational two spectra is called equivalent to what I'll call K-top cell S hat modules. So what do I mean by this? Well, for each one of these things, I can look at EF modules in rational SO2 spectra, and the same here. So I'm going to delete this here. So if you look at this diagram, what do I mean by K-top? Well, I take off the modules and I just smash with the compact generators category. There's a quantum equivalence, it's symmetric monoidal, and then there's some what I'm going to call magic that I still don't quite understand. And then we get this abelian category, which is the algebraic model of SO2. I'm interested in this step. I don't really know anything about what happens this side. So this was for the circle. This has been done for O2 by Dave, SO3 by Magda. John and Brooke have done this for the torus. We see that the key point is really these pullback squares, and for Tn, we have a homotopy pullback n cube. So we're not always working with squares, we're going to have n plus 1 cube. Right, so this is kind of the motivation. We want to see how general these types of pullback squares are, and then can we start making some Quillen equivalences between categories of interest and maybe some nicer categories here, depending on your definition of nice. So the key insight, which I'm going to attribute to John here, is that these homotopy pullback n cubes, these are indexed on the Balmer spectrum of the homotopy category of Tn rational spectra. And we're going to use this. We're going to look at some tensor triangulated categories. We're going to look at their Balmer spectrum, and we're going to construct these type of local complete pictures using the data of the Balmer spectrum. So for those of you who weren't at Toby's talk on Wednesday, I'm going to just reiterate what the Balmer spectrum is. I'm going to define what these Noetherian model categories are, and then I'm going to show how we can define these type of pictures in general. So let's move on to the first actual section, which is Balmer spectra. So what do we have? T will be some tensor triangulated category. So tensor structure, apple its triangulated structure. We say T, a thick tensor subcategory, is prime if A tends to be P implies that A in P or P. No surprises there, it's exactly the same as the prime condition for normal ideals. So this was work of Balmer, who first started looking at these, although this type of structure, I guess, has been studied for a lot longer before then. So what can we do? So we can find the object SPC of T. So this is the set of prime ideals. Well, I'm going to set a collection here, I guess. So if we look at the collection of prime ideals of some tensor triangulated category T. So this has a Zariski-based topology using support theory. I'm not going to go into that. For now, we're just going to care about we can have inclusions of these prime ideals into each other, and this is going to be our key kind of object. What also will be important for us is we can look at the closure of points under the Zariski topology. So I can look at prime P, I can look at its closure, and this consists of those primes Q, such that Q is contained in P. This is going to be an important object later on. So just having a TT category is way too general for what we want to do. So I'm going to use some new notation here. So SPCC of T. I'm going to let this be the Balmer spectrum of just the compact objects in T. So this is like moving from all modules just by finitely generated modules. This is all better behaved. I'm going to ask for T. So T needs to be rigidly compactly generated. Which just means that my collection of compact objects and my collection of strongly dualizable objects are going to coincide. So this is just some finiteness condition which makes everything work a lot nicer. So I'm going to have add more conditions onto T here. So this is my first one, and the second one is something to do with the structure of my Balmer spectrum. So I'm going to ask that this SPCC of T is a catenary Noetherian, and I think I'm going to stick finite in topological space.
What is catenary?
So, catenary, this means I have a well-defined dimension function. P goes to dimension of P. So this is well-defined. This is what catenary means for us.
Is that how you pronounce it? I do pronounce it
So, unfortunately, just having Noetherian topological space isn't enough to ensure catenary. So, I believe this was a result of Nagata, who made an example of a Noetherian ring which was not a local Noetherian ring, which is not catenary. So, I'm going to ask my.
Sorry, what does dim P mean?
So it means I have a well-defined function from SPC of T to, let's say, natural numbers. It lets me define a dimension to my primes.
Okay, what do you mean? I mean, why not just a zero function? I mean,
Oh, right, okay, yeah. So I mean, it also means
some properties.
that the length of any, so if I have primes P and Q, then the any chain of primes linking them has the same length.
In maximal, so, yeah.
Maximal chain has the same length, yes.
So it's more than just being, I mean, you could take the max, right? So you can easily define a height function also for non-continuous array, right? It would just be, have jumps.
That doesn't have anything to do with the dimension function. That doesn't mention the dimension function.
No, but having it allows you to define, say, a Krull dimension on your ring.
Okay, do we have a condition, for example, if one is properly contained in the other dimension has to go up? Do we have something like
Yes.
this? Okay.
Everyone happy with catenary?
Not really, but go on.
Okay, so this Noetherian is going to be really important for us. So bearing in mind we're going to want to do completion at some point, or some notion of completion, you'd expect an Noetherian assumption to be floating around, hopefully. So what does it Noetherian means? There's a lemma.
Wait, one more thing, does it finite? Does this mean sort of finite dimension or
Finite
many
dimensional
altogether?
topological
No,
space.
just finite dimension.
Yeah. I can have infinitely many primes, but as long as they're all finite dimensional. So it's probably lemma Balmer, but it's also not hard to show. So if your Balmer spectrum is an Noetherian topological space, then this means that every closure of prime P is detected by the support of some object H. So I haven't defined support, I'm going to do that in a while, but we're going to need this. We can pick X to be compact if we want, but it's not actually going to be necessary. Right, so then what I want to call a TT category, which is rigidly compactly generated with catenary Noetherian finite topological space, is just going to be excellent, because I want to see this as a categorical analog of an excellent ring. Okay. So this has the really unfortunate, well, depends how much you like reading Lurie, that I'm going to want to detect these TT categories by homotopy categories of the model categories. I've called these excellent, so what's the appropriate name for the model categories? I want to call them excellent model categories. In Appendix 3 of higher topos theory, there is the notion of an excellent model category. It has nothing to do with this, unfortunately, but sometimes some names. I think excellent works well here, but
It's excellent.
yeah. I mean, as far as I'm aware, Lurie's definition of excellent is just because they're really, really good. You know? Whereas this is like, it's like an excellent ring. Yes. You can't have smashing, so you have smashing localizations.
You could call them really, really good.
Really good. Extraordinary model categories. So anyway, let's have some examples of such things. Let's try and add some examples of this. So that are the commutative Noetherian ring, of course. Then I can look at the derived category of R. This is a TT category, and it's well known that the compact Balmer spectrum of the R as kind of sets is the same as Spec R in the ordinary sense. However, the ordering is reversed here, so that R be Z, and I have my zero ideal, so this is now my largest ideal. Okay, so the ordering changes. This gets very annoying when trying to sometimes talk to John about this, who loves commutative algebra. Everything gets messed up. So, a bit more exotic. We can
Didn't
let-
you say a little bit earlier the examples of Noetherian rings where it's not catenary?
Yeah, so I should really have excellent theory ring here. So my second example, let X be a catenary Noetherian scheme. So Noetherian here, I want topologically Noetherian. Then I can look at coherent sheaves on X. And it's well known that the kind of Balmer spectrum of this you can use to recover X. In the first place, I think this is work of all of reconstruction theory, that's way back to when this kind of result was known. We can have X a diluted monthly stack. Let's look at characteristic 0 for now. And again, plus coherent. She's on the stack. This is a suitable category that's going to run through our machinery. This works in characteristic non-zero, but then you have to ask your stack to be tame, if you know what that means. So let's move away from this type of example. So G a finite group. K a field with characteristic K dividing order of G. And the stable module category works.
Can I ask you, in two, so you say that you recover X, do you recover the scheme or just the underlying?
You can
space?
recover the whole scheme from this. Yeah. I'm not aware if there's a similar result for the stack case. So this has been computed. So this is just the projected scheme on the group cohomology G with coefficient K. So I've got quite good grasp on this one. So maybe the only example that most people in this room will care about is, the ordinary category of spectra. So this is not an excellent TT category. Why? Well, I have primes at infinite height, that's the first issue, and these primes of infinite height aren't actually detected by the support of any object. So this doesn't work, but what I can quite easily do is take LEN of the category of spectra, let's fix a prime. Then I have my kind of torsion guys. P2. And up to my prime. So these are the kernels of the Morava. So this works. And then obviously it would be a shame to not mention the example, so SBQ of G. But here, G has to be a torus. So what's the Balmer spectrum here? So quantity glasses. Subgroups. And the Kotor inclusion. And this is a result of John. So it's a shame that at the moment you can only work with tori, but hopefully we'll fix this in the end. So let me show why, say, O2 doesn't work here.
So what does cotoral inclusion mean?
So cotoral, so K in subgroup of G is cotoral if G mod K is a torus.
And how is this a space?
How's this a space, sorry?
So you're saying that this is a space?
Yes. So you've got this set, and then you can use support theory to define what the enclosed set should be. So it's called a Zariski type topology.
What was this cotoral inclusion relevant for?
So the point is the inclusions of primes in the Balmer spectrum isn't just ordinary inclusion of subgroups. It has to be cotoral inclusion.
So that refers to this topology on the space?
When you have an inclusion.
This has nothing, it's not like the subgroups have to be cotoral in the big group or something, so they have to be connected. Well,
I mean, they've got to be cotoral in the big group as well.
that's because everything is.
Sorry?
That's because everything is. In a torus, every subgroup is.
Oh, right, yeah, so this is, yeah. So this is the general result for any.
So the definition of the point stops after subgroup.
Yeah.
Okay.
Because, so this definition works for any compact Lie group. So that's what I've written down for any compact Lie group. Is that a correct statement, John?
Yes, I mean, and the order relation under, if K is a subgroup of H, it's cotorr if it's normal, and the quotient is a torus. I mean,
Right.
And it's all subgroups, they don't have to be cotorr group.
So just a brief remark on O2. So I'm just about to say why this is important. So we can't have things like O2 for the following reason. So the Balmer spectrum here splits into two pieces. It's got the SO2 piece and the actual O2 piece. And what we have, the dihedral groups, so D2, D4, D6, and these all converge to O2. So this point O2 is not separable. So I can't detect this point by the support of some object. So you only have this condition if you are a torus. Okay, so O2 for now doesn't work in our machinery.
So what you say is the Balmer spectrum is always that by view of John, but only when G is a torus, you got an excellent guy by your definition, right? Is that what you mean?
Yes.
Okay.
So X and C you only get for a torus, absolutely. Okay. So we have to move to model categories now. I assume most of what I'm about to say you'll be able to rephrase in infinity categories if that's where you like. So I'm going to say that a model category C is excellent if the homotopy category of C is an excellent T category. So in the work of people like Hovey, Palmer, and Strickland, they thought about basically just type thing before, we're just adding some extra conditions to control the behavior of our Balmer spectrum.
Are you asking for a symmetrical ordered product before deriving, or
Yes.
only after deriving? Okay.
Before driving. So I'm just going to write down briefly what kind of conditions you want here. So I'm going to want it to be cellular, proper, stable, symmetric anoidal, compactly generated. What else right here? And then carry on from this, so the unit has to be cofibrant and compact or small. And then the other thing that we need to ask is, I'm going to denote it this. So this is the Balmer spectrum of the homotopy category. This just needs to be continually in Noetherian. And I don't know any way to detect this on the model category structure. I think you have to pass the homotopy category and then compute this. So this kind of is
Well, it's only an invariant of the underlying quasi category anyhow, so how could you detect it?
yeah, exactly. So this just has to go as an extra thing on the end, unfortunately. You don't have a nice thing saying anything like that. So these are the, so then there's also some more plus extra, just some horrible things regarding cofibration as you'd expect.
So we have one more question about the O2 case. So
Yeah, absolutely.
You said it's not excellent, so which of the two conditions failed? Or of the kind of work done, you said something was
It's not an Noetherian topological space.
not in the theory to work.
Yeah, because we have this non-separable point here. So we have these model categories, and now the idea is you want to kind of define the idea of completion and localization on these using the Balmer spectrum. And what I will say is all of these examples come from excellent model categories, right? So this is the projected model structure and chain complex of R. This is the same for chain complexes, same for the stack. This comes from the stable model structure on modules. This obviously is a model structure, and so is this. So all of these are detected by excellent model structures. So even though it looks like we have a horrific amount of conditions here, they are at least satisfied sometimes. Okay. So what I want to do now is look at completion and localization. So by localization here, of course, I mean Balchin localization. So I'm going to let C be X the model category. And P is going to be a prime in Balmer spectrum. And what we want P complete and P local things. So people like John and Peter May, Dwyer, and a lot of other people have done work on complete and local things, and it was just a case of unwrapping it to this model category level of the Balmer spectrum. And it turns out the correct thing to do is the following. So the first one we have is LP, which is the localization. So this is the Balchin localization. Following. So remember, P is some thick subcategory of our homotopy category, and I can look at the objects in here and I can nullify them. So this is nullification. This exists because of our compactness conditions. This is a small subcategory. So this exists, that's fine. This is kind of a Hirschhorn style localization. Lambda P is a bit more exotic. So this is the Bausfield localization at some object Kp. So what is Kp? So Kp is the object whose support is the closure of P. So here is exactly where I need my Noetherian condition. If I didn't have my Noetherian condition on the Balmer spectrum, I couldn't find this object Kp. Okay. So why does this exist? So I'm doing kind of homological style localization at Kp. So it turns out that these conditions I've written down here are the exact conditions on the category spectra that you use to do homological localization on the category spectrum. So you just kind of unwind enough to get what you need, and it turns out that these conditions are sufficient for this. So this is my P localization, and I've got my P completion.
So is the LP like LN localization and the lambda like KN localization?
Absolutely is.
But then you don't need the object KP to talk about KN localization. So this is not
No.
a strong reason for saying we must have this.
So I think we can probably get around the Noetherianness at some point, yes. So yes, it could work, but this is kind of the same as if you want to do completion of rings, you probably learn how to do it for a Noetherian ring first before troubling yourself with non-Noetherian things. I think this was probably the idea.
I mean, the point here is that this Kp is compact.
Yeah, we can take Kp to be a compact object. So this also helps, and it's gonna, well. So there's also another reason why this might be interesting in a second. So the first thing I do is maybe talk about what this Kp is. This lambda P, sorry. So examples, chain complex of Z modules, and let P be some prime P. So the thing to know is that lambda P, so Kp here will be Z bar P. So if I apply localization here, so what I want to point out is these two things are not equivalent. So these two things are not equivalent. If I were to apply lambda P here, it would be equivalent. So this here you should see more like chain complexes of ZP hat modules. But here I'm killing Q this is more what this object is like. So it's not nice. These localizations are not smashing. These ones will be smashing. So yeah, exactly like EN, KM type of plot. And we can prove some nice lemmas about these things. So if P is Balmer minimal, and minimal primes won't exist, then LP lambda P is the same as lambda P. Wow, indeed, if you take P completion of the integers and then localize at P, it's the same as just doing P completion. And then if P is the unique, if P is such, so this is probably the worst way of writing this. What I want to say is that my Balmer spectrum has one maximal prime, let's call it P. Then we have that completing at this maximal thing is the same as doing nothing. Completing at 0 of the integers is the same as not doing it. So these are the things there. So, Stefan, this might answer your question now. Why do we want to define it in this way with this object? So the idea is everything's going to work because of co-support theory, so support and co-support theory. So I'm not going to define what either of these things are. I'm just going to give a lemma, which, well, theorem. So this is Benson, Kedziorek, and Krause. And they state that the minimum of the support of an object, compact object X, is the same as the minimum of the co-support of an object X. And it turns out this theorem is the exact reason, for example, why the Hasse square is a pullback. It's the reason why the Tate square is a pullback. And it's going to be the reason why all of the theorems about this state work. And to be able to do this machinery, you need to have access to this object KP.
What does minimum mean?
This minimum as in, so this will be a poset, and you can take the minimum object there.
And do you want to give us any more information on what co-support is?
I don't want to off the top of my head because I'm getting it wrong. But this is, the support was defined in this BIK paper for commutative rings. All you have to do is swap the ordering to get it for TT categories. But this is a really, this relates to a complete thing, so completion of complete things. So it's a bit horrible. But this is why everything works.
So
Yes,
if
yes, please,
if
John.
I take the cellularization of P,
Yeah.
That's the gamma P, and then I localize at P, so that's an object. I pulls out of that a non-trivial, so now P is in the co-support. So BIK have done a terrible thing with notation, so they just call that localization of cellularization. They just use the letter gamma, so they can confusion. And support is you take that object and you tensor it with the thing, if that's non-trivial. P is in the support.
Yeah, I blame BIK for how scared I am of it.
It was homing out versus tensor.
Exactly.
So in fact, I've now got all the machinery I need to state the results that we want. So the idea is we want to build a unit out of these lambdas and L's, and then we're going to build some sort of module model based on these. So if I can get the So there's two things we can do here. So one is inspired by what John and Brooke have done, and the other one is inspired by kind of higher local fields and higher Adels. So I'm going to give the kind of Greenlees Shipley approach. So in section 4, Adelic models. Here's a theorem being done, which I guess we call the Adelic approximation theorem. So I've got something to refer to. So it says that the monoidal unit in C is the homotopy pullback, or the homotopy limit. Of the H of n cube. What's n here? N is the topological dimension of my Balmer spectrum. So, whose object at position right, let's try and fix it nicely. So here I've got some product, it runs over primes P0, whose dimension is D0. And I'm going to take the localization. And then here, I'm going to take dimension P1 is P0. I'm going to ask that P1 is contained in P0. So I'm looking at flags here in my Balmer spectrum. And then I carry on such process. So here I just have L's going on, but then at this final term, I'm going to have the following. So this is what the vertices of my cube are look like. I'm going to draw an example of one of these in a second. But we only have the completion at this final term here. We don't need completions anywhere else. And these are all just localizations.
I think this P0 should be a D0.
So this is for any excellency.
So this works for any excellent model category C. So I mentioned another approach to this, so I'll just briefly kind of note what it is. So in this position, I'd instead have this, so lambda PS LPS. Here I would have lambda PS minus 1, LPS minus 1, and kind of here I'd have lambda. So this is kind of an alternate thing you can do here. We think we can prove this, but we do think we can prove this, right?
In computed algebra, we can prove it.
Yeah, intuitive algorithms. So these terms here are really inspired by write some words here. So Balmer's So Balchin wrote this kind of one-page paper in Russian a long time ago about higher dimensional Adels, and Hasse came along and proved that actually any of it works. And this is the kind of terms that they have in these higher dimensional Adels, and then there's a lot of work going on at the moment in these higher level field theories. And the idea is if here I was looking at chain complexes of R modules, and then the unit here, this object itself would be one of these higher dimensional local fields. I have no idea what's going on there, but maybe one day I will.
Can I ask you in this case with the Tate
Yeah.
thing, which one of them is L and which one is the head?
Yeah, so I will write that down now. So I would rewrite the Tate square as follows. So let's do some examples. So C. So it's saying I look at the following. I have L T of sphere spectrum. So what I should do is say what this Balmer spectrum is. I have SO2 here, which I'm going to call T for brevity. Then I have the cyclic groups running through like this. So I have LT as S0 here. Here I take the product of the N of lambda C N of S0. And here I have LT of the product. So this is what the Tate square looks like in this language. You work out what the image of the unit is under here. So this becomes.
So can you say what LT is in more concrete terms?
That's what it's
I was doing now.
Yeah, so this will be e to the f. And this will be the product of these DE 20n classes, which I've already stated. Okay. Then this is e to the f smash this product. So this retrieves the usual Tate square from SO2.
Why in this case are all the localizations homological?
They're not. LT is a prime here. Right? I've said SO2 is a Balmer prime. And my notation for this is this, L sub P for the prime. This isn't a homological style localization, this is a nullification.
But it actually is.
I mean, it is a homological localization as
I
well.
think that's because it's maximal.
Yeah. I think seeing as I have maybe enough time, I'm going to go to the effort of just drawing out what this even looks like for dimension not 1, just so you have an idea of what's going on. So I'm going to write in my. I'll start by writing in the unit, just so I can keep track of where I am. So I'm assuming here that I have a maximal, one single maximal prime, just to make the bookkeeping a bit easier. Here, and then I'm sure you can probably fill in what that last gap is. So these are what these kind of high dimensional cubes look like. We have a mixture of different fragments, so pi are primes of dimension I here. So this is what, if you look in John and Brooks' paper on the torus model, the algebraic model of torus, you'll see a picture just like this, but reworded in kind of equivariant. So great, if I actually write the unit as what can I do, horrific looking diagram, what we're going to do with it? Well, we're now going to build a model, I'll call it an Adelic model. So the theorem is as follows. So let's see be an excellent model category. So we know that this is going to have some compact generators, homotopy category. So denote by G. So these are just exactly the cofibers of the generating cofibrations. And then what can we say? So if I denote by, so I'm going to denote this entire cube by one open box. So it says I've got Coulomb equivalence like this, so Coulomb equivalence between G smash one box. Celerization of one box. So I look at modules at each one of these vertices. We're not sure in general, and I doubt it's true, that these are going to be commutative ring objects. So this is not going to be a monoidal Coulomb equivalence. But if each one of these vertices is a commutative ring, then we can say this is a monoidal equivalence. So if you refer back to at the start when we said about the algebraic model for the circle.
So are you saying localization? Which of the localizations or completions is possibly destroy the property of being commutative ring objects?
None of them are.
Why did you then say it's not a commutative ring?
I mean, but isn't this the fact that E tilde ref is hard to prove this is
Oh, this is, you mean,
Yeah.
you don't mean commutative, you mean ultra commutative.
Ultra commutative.
Well, you know, if I think in terms of infinity categories, this is commutative.
Right, okay. So whatever.
And you know, you didn't say that you're in a model category where points at level commutative things have some special meaning.
Yeah, that's a perspective.
So
So if you have some sort of good idea of commutativity or ultra commutativity, then you might be able to say something about this, but in general we can't, is what I'm trying to say here. So this is the result. So this does give you possibly the worst, well, I don't know, you can build the category of abelian groups using this, right? You can look at the following. So it says that chains of Z modules.
So one more question. So the
Yeah.
generators, it's not really an intrinsic thing. Can you also explain the right-hand side of the equation in more intrinsic terms?
This.
Generators is a choice. You could make
Yeah,
different
it is a
choices.
choice, absolutely.
Yeah.
So I'm making a choice of generators using my generating cofibrations.
But cellularization doesn't depend.
Exactly, that was my question. Cellularization doesn't depend on it. So
Yeah, I mean, I'm making a choice, but the choice is not important. I could have taken, I want these to be compact, so I can't just take the wedge of all of my generators, because that's not going to be compact.
So are you simply taking the localizing subcategory generated by all compacts? Or
By the
something like
images.
that? The images of all compacts. Okay, yeah. Okay, thank you. So,
So this is a construction of the category being groups, right? Yeah, I can take this. This is the Hasse square. Well, we know the pullback of this is Z. So this theorem is telling me that I take the generator, well, the generator I just take to be Z, so I smash it, I get this. I cellularize this, so I have Q modules, Z hat modules. This should be Q tensor Z hat modules, of course. Okay, so this is kind of an example of what this theorem tells us. So why is this interesting? Well, the first step of these algebraic models was doing such a thing, and we can do that out in generality. There's also some other questions we can ask in my notes. Okay. So, some other examples you might care about. So if I look at L, En, category spectra, then these LPs are going to be the same as kind of L, E, and Fs. And lambda P's are going to give you something along the lines of L, K, Ms. So, I mean, this is exactly what Toby's done with Omar at some point around these fracture cubes of chromatic things. So these will give you these chromatic fracture cubes. And then in the last 5 minutes, maybe just a word about fixing some of these Noetherian issues. So we've already established that maybe I don't need Noetherianness to talk about things like K localization. Sure. But then how do I deal, well, not how do I deal with things, but let's go back to this O2 case again. So the problem was I had this I've got O2 set here. I said that I can't separate O2, so how can I deal with this? Well, the solution that Dave came up with, so Barnes, is you detect O2 as a colimit of the dn bits. So you can detect this O2 part by doing sort of a colimit of the dn's. And what we want to do is kind of generalize this to kind of model category C, where we have this non-separability condition. It seems like it's going to go through quite nicely. But more interestingly still, so what we've done here is we've defined these localizations. I've looked at the image of the unit under the localization, then we've constructed these models. Well, what if we kind of bypass all of that? So here's a very tentative suggestion. I could look at my category C. I could just look at L P naught C. Let's assume I have a maximal prime. We would like to be able to define such a diagram. So now instead of looking into the unit, I mean, I actually have an infinite product of model categories here, which itself is a model structure. And we'd like to be able to define this in such a way that this is somehow a pullback. I'll put this in. I'll come with some sort of pullback of model categories. So this would be kind of the work of Judy Bergman has done bits on this. I mean, another solution to this would be to start working with infinity categories where the pullback actually makes way more sense. Stefan is thumbs upping, this is good. So, I mean, this is something on the horizon.
I'm already earlier.
Already on board with that, yeah. Yeah, obviously, infinity categories is probably where eventually we're going to want to take this. And one last thing I want to talk about is this type of thing. So let's look again at the equivariant case. So I could look at the product of L E pointy n. So T is the circle here. So I can do this, but we also know we can do something like this. L So I can either localize each E pointy n homologically and take the product of these, or I can just look at LEF. So this is the same as what I was saying earlier about that the product of DZ and no classes. So somehow I have these two things, and I know what I can do is I can do this LT on this side. And I also want to do some sort of LT here. I'll make this a equivalence. So if you've looked at any of the stuff that maybe John or Brooke or people have done, we have this cellularization principle, which is a right boundary localization, which under certain conditions can change a equivalent adjunction into a equivalent equivalence. And it looks like what we're going to need to do if we want to talk anything like this in the model category sense is we're going to have some sort of left version of this cellularization principle. So So if no one because polarization principles that would make any sense. There's a lot of left Balchin world where this works. So I think I'm going to stop there.
Thank you very much. Are there some more questions? Everybody seems to be extremely happy and content, as far as I can tell now.
I'm surprised in this last corner in this diagram that the lambda and the L is not in the opposite order.
This one here.
Yeah.
So the reason I'm writing like this is because that's how we have it in this Adelic approximation theorem. But the fact that these L and lambda should be switched around is quite before, right? So
Did the Hasse square, they come this way.
yeah,
They were. They come this way, that round.
yeah, you want to look at the image of the unit under this, and you want to retrieve the Hasse square, for example.
But in the Bayes
It's
and
just
Moshin
really-
approach, they go for another order. So it seemed to work.
And also in the
The take square is this way. LT is the heat. It's actually going to be to the rack.
Yeah, there's definitely some discussion to be had of the ordering of these.
Well, I mean, I would like to point out that we proved the version right. I mean,
Yes.
with,
Yeah.
I mean, with
But
you here and
have
Gabriel
problems
Taylor, we have
with the
We have a
problems.
pullback, well, not quite this version, but I mean, a version of that were actual stable infinity categories.
Because I thought you did it when you
No, not for the products, but I mean. if you-
Without the
if- if-
products, it's easy though, right?
Fair enough.
So why is it easy? Well, I mean, what's an object here? Well, it's okay. I mean, it's a tuple, right? And how is this localization going to act on a tuple? Well, you don't want it to act on each. You don't want it to act coordinate-wise, because this is the difference of Q tensor that we have and the product of. If you let this localization act coordinate-wise, you get p-adic rationals. So what we need to define is some sort of Adelic left partial localization. But yes, Toby and authors have done this where you don't have the products, yes. Using infinity categories, of course.
More questions? Thanks, Scott, again, and close the